Okay, so before you start your CFD model, you need a model of it. So this is kind of a bit of a silly way to do this, but I just thought I'd show you for something more complex. So I started, in any simulation software, you can have symmetry. So this is why I made this. This basically is supposed to be a section of the fuselage. When the airbags are deployed, it has 1/3 symmetry. So basically, when we model the flaps deployed, there'll be this will model one flap. Yeah, so basically, I just first thing split it into 3. Basically, you should exploit symmetry whenever you can, because rather than modeling the entire thing, you model 1/3 or 1/2 of the thing, and it's a lot better. So this is your thing that you want to model. Next, you have to actually model your fluid domain. So I did that by basically creating this second boss extrude. Basically, if you look at the sketch, it's just a bigger version of the fuselage. Sometimes you'll see people do a square, sometimes you'll see people do a circle. Because this is a circle, I did a circular domain. If you want to model the flow before and after the object, you need to make it bigger than the object. In this case, I just want to model a section. So it's okay that the object basically touches the fluid domain. But if you say wanted to do an airfoil, you'd want to leave some space at the rear and front side. So we have our part that we're modeling and then our fluid domain. When you do this boss extrude, you have to uncheck merge result, because basically what this will do is create 2 separate bodies. So in this case, it's kind of extraneous to do this. We could just model the fluid domain, but if you had something like fins sticking out, we pretty much want a negative mold of what we're trying to model. So if you have fins and stuff, it's very hard to create a mold with that unless you pretty much subtract the 2 bodies. So that's what the next operation does, combine. So once you have your part and then your domain, it's under here, insert features. I actually can't. Oh yeah, it's grayed out because there's only 1 body, but once you have multiple bodies, this combine option will appear and you hit combine. When you go edit feature, you can see, so the main body is your fluid domain and your body to combine is the object that you're trying to simulate. And if you hit subtract, basically what it does is subtract this second body from this first body. And so once you do that, you have a negative mold. If you had, say, a fin or a flap sticking out, it would also cut a negative of that. So you pretty much have your fluid domain around your object. You go ahead and save that. And you also want to save as a step file. So save as type step, and make sure you hit options and make sure this split periodic faces is unchecked. I already saved that, so we don't need to do that. And so once you're happy with your model, you can open up ANSYS. So you have to search Workbench is what you want. There's a bunch of different ANSYS packages that will get installed, but what you're looking for is Workbench. We good so far? Did that kind of model explanation make sense? Okay. Yeah, so pretty much what you feed ANSYS is not your part, it's the fluid around your part. So then this is what appears once you've opened ANSYS. So there's a couple different like CFD options, the main two are CFX and Fluent. I'm only familiar with Fluent, so that is what we're going to do. I think it's better for supersonic flow, I believe. So pretty much it brings up this box. You can connect multiple phases, like you might want to connect a CFD simulation with like a FEA simulation. We're not going to be doing that, but just so you know, you can do that. And for most ANSYS simulations, this geometry and mesh is kind of the same throughout. Like it's not specific to like necessarily like a CFD simulation. So for geometry, if you right click, import geometry, you can just browse for your part. So this one is the step file. We open that, and that's it. You can make your geometry from scratch, but it takes a long time. You should just always make a SolidWorks model, basically. So the next step is mesh. So we double click on that, and we'll open up the mesher. And the mesh is basically how you split up the domain for it to calculate. So the smaller mesh, it takes like smaller elements, which is usually more accurate, but more computational power. There's also some limits because I believe this is academic. Yeah, it's a student license, so there's a limit on how many nodes you can have. So I'm going to go ahead and save this first. So yeah, you'll notice this is the workbench, and then the mesh opens up in a separate window. So how you navigate around, if you scroll in and out, and then if you hold the scroll wheel, it will pivot this. So this is the selection. So smart select, it kind of just like tries to figure out what you're selecting, but you can set it to vertex, where it will just pick up vertex, vertices, edge, face, or you can select the whole thing. So mesh, so if there's a lightning bolt, basically it means it hasn't been like updated. So if we just, first thing I always do is generate the default mesh. This is not a very fine mesh, but it's pretty, you can see it's like pretty well ordered. So basically what I'm going to do is just make the mesh smaller. So if you right click, insert, so you can do all these things. We're going to insert sizing. So the yellow is where you need to select. So geometry, we want to apply the sizing to the whole body. And then you hit apply. I pretty much leave all the defaults except the element size. So you have to kind of play around with this and potentially change it after your simulation. But I'm going to set it to 0.005. I think that's what I had. I tested this and it worked pretty well. And so has not updated again. You see there's the lightning bolt, which means you need to right click update. And so there's your mesh. You can see it's a lot better. We can maybe go a little smaller, but for the sake of time, I'm gonna leave the mesh like that because it won't tell you you've created too many elements until you get to the very end. And sometimes it takes also a very long time to generate the mesh. But one thing we could also do, so the mesh will be most important right next to the fuselage, basically. So you can also insert inflation, which basically just, so geometry will be fuselage, or sorry, the geometry will be the whole body, and the boundary will be, oops, I messed that up. Yeah, so the geometry is the body, and then the boundary is kind of the edge that you want to refine the mesh around. I pretty much don't mess with the amount of layers and stuff. And if we update that. It's kind of hard to explain what it does, but you'll kind of see it will create like these small layers like right next to the fuselage. I actually do not like that. I'm actually just going to go back to what we had because I think the mesh was nicer. This is all kind of trial and error. Yeah, so you can see it's pretty small. It's pretty like well ordered. The elements are of similar size and the elements have like a decent aspect ratio. So basically if you're like poor quality elements will be kind of like have a big aspect ratio where one dimension will be really long and then it will be like really skinny, say. But this default mesh looks pretty good. So save. And then the second thing you have to do in your mesh is kind of name all your sides, which I will just show you and hopefully it'll make sense. So if you right click on a side, you can, or if you click on a face, right click, create name selection. So I'm going to call this inlet. Okay. It doesn't really matter what you call each side of your object as long as you remember which one's which, but typically you have an inlet and then on the other side you have an outlet. So flow goes in one way, out the other way. This is where basically the fluid touches the fuselage. And so that I'm just going to call this fuselage. And then these two edges are the symmetrical edges. So I'm going to call them symmetry. Symmetry. Now the only thing we haven't named is this outer edge. And I'm going to call this I don't know, outer domain. So basically for each side of the model, I've given it a name. In some cases, you might have multiple faces that are called the same thing. For example, again, if we had a fin, you might select all the faces of the fin and just call that fin. But yeah, generally you always have an inlet and an outlet. You'll have various selections of things that are like your wall. Then you might have some symmetry edges, and then you'll have your outer edge. Any questions before I move on? Okay. Oh, good. Yeah, if you ever run into problems with meshing, just like a general ANSYS, even if it's an FEA or a different tutorial, will be helpful. And then, yeah, for some reason it doesn't like load the mesh. If you just right click update. And hopefully runs. So the reason we name all those sides basically is because we're going, in the next step, we're going to be feeding it boundary conditions. So basically numerical solvers use like basically differential equations to solve things. So it needs like boundary conditions. And so you give it, for example, you get a, like an inlet velocity or an outlet pressure. And so it knows a condition at each of the boundaries. Okay, there we go. So check mark means it's solved. So now we can go to setup. So you can double click on it. And now this is how we actually get into Fluent. The first two steps are just pretty general ANSYS. So I always hit double precision. If you know how many cores your machine is, you can have multiple processes going at once. I'll just leave it at 1 for now. So now we're in Fluent. Okay. So this is probably the hardest part, just because there can be like a lot of settings. It can be a little intimidating. So it will import your model with you. And when you name stuff, it will guess what the names are. So when it sees inlet and outlet, it will just automatically kind of guess where the flow is going in versus going out. So if we go to models, this is basically all the possible models you can apply in Fluent, because you might not be just looking at drag and stuff. You might be looking at like heat exchange and stuff, and other things. Basically, all the CFD models are under viscous. It seems like either the K epsilon or the K omega or the Spalart Almaraz are typically used. I don't think there's like a hard and fast, like which one's the best. They're basically just different like, equations the solver uses. So I'll just leave it on K epsilon. So this is I guess I should also mention a steady simulation. Basically means like it doesn't consider changes over time. Basically just at an instant what's going to happen. You can also change, you can change the solver to be density based or to have relative velocity. I'm going to leave them at pressure based and absolute. I'm not sure if it matters too much in this case. Materials, so for fluid, it automatically selects air. And that's good. I mean, technically we can edit the density because this will not be at sea level, but I will leave that. Solid, unfortunately, doesn't have a ton of solid material options. Like if you sort by solid, I mean, this is all there is, so I will leave it as aluminum. I don't think it really affects too much. I think this would mostly just be heat transfer. In our case, the air brakes are aluminum. It's just the fuselage is not. And then basically this is just showing that the whole, so cell zone conditions, fluid, basically this whole part is fluid. Sometimes like in the past, I've tried modeling a solid domain and a fluid domain, in which case you get a solid drop down as well. That doesn't seem to work very well. So you can just leave that. Generally, you don't need to change materials, cell zone, or we need to double click on boundary conditions. So it imports basically all our named selections. If you're confused, like if you accidentally misnamed something, this like display mesh is pretty helpful. So it displays like inlet and symmetry. You can just display whatever you want. So fuselage. So the fuselage, the type, it automatically set to a wall, which is good. I'll just open up. We'll keep it as a stationary wall, and it will be a no slip wall, which basically means the particles like on the wall, like when they hit it, they do not slip. That's a pretty standard assumption. The inlet, it automatically identified a velocity inlet, which is good. That's what we want. We want to give it an inlet velocity. I think we're going to model this at 0.7 Mach, or at least that's what they previously did. So we'll first try to validate on the old results and then maybe look at cranking up the speed to our max speed. Yeah, usually just keep absolute and keep all of that close. This is just literally the interior of this is just like basically this entire body, and it's just saying it's the fluid, I believe. Yeah, it doesn't do anything. Outer domain. Okay, so this is one you have to watch because it will automatically import it as a wall, but this is not a wall. This is pretty much like a free stream. Like hopefully you've made your domain big enough that by here, there's kind of no pressure difference. So one thing that sometimes people use is the far field pressure, which just says like on this domain on either side is basically like the free stream. I could not get that to work. So another thing that also works is symmetry. Because symmetry basically says this is like on either side of this like domain is the same. So pretty much we want to have like no disturbances on the outside of this. So there should, if you cross that domain, it should be the same. Outlet is automatically a pressure outlet. Which when you open that up, you can pretty much give it a pressure at the outlet. So the automatic is 0. So we will leave that because it basically means there's no disturbances pretty much, like you've pretty much returned to the normal flow. And then these two symmetry just automatically import a symmetry, which is good. We don't need to do anything with those. Reference values. So you don't need to change anything else. Reference values, if we double click on them. So basically it calculates, we're looking for drag coefficient, and drag is always relative to an area. And in our case, our reference area is the rocket, like diameter, like the main kind of diameter, I think is 0.0109 meters squared. The density is just the density of air. Also you compute from the inlet, and so we'll automatically import the velocity inlet. I just leave everything else, and then the reference zone is just your domain here. Yeah, generally for this, I don't think we need to change length or anything else. Again, a lot of these are for like heat transfer and stuff, which is not super relevant. Let's save. Okay. So you can change the solution method. I mean, you can probably look at playing around with this, maybe do some research into what's best for this simulation, but for now I'll just leave the default solution. We are going to add report definitions. So basically we want to get values out of this. So if we hit new, force report is what we want. So we want drag. It opens up this dialog. I want specifically the drag coefficient. And we want it in the Z direction. You can see there's a little coordinate system here. So we want it along the fuselage, which would be 0, 0, and it's actually in the negative Z. You do have to watch that. If you get a negative drag coefficient, check that your vector is the right direction. I'll call this fuselage CD. And we can also, just for funsies, also export the force. With the force, you have to be careful when you use symmetry because it will just be the force on that. You have to be careful with your like reference area and stuff. I can't quite remember if it will report the full force or the 1/3 force, because our reference area is for the full rocket, not for the third. So You do have to check that. So call this use track. So now we have our things that we want out, basically. Initialization. So pretty much just hit initialize. What this does is kind of runs a couple of iterations just to get started. And now pretty much you're ready to run your calculation. Maybe I should stop. Do you guys have any questions? Okay. So hit run calculation. I don't know, let's put like 1,000 intervals. Again, I just leave all of this and hit calculate, and it hopefully does not throw any errors. Okay, perfect. So now what it's plotting here, so your residuals are pretty much your like error. Continuity is conservation of mass. XYZ velocity, I believe, is related to conservation of momentum. And then K and epsilon is related to, we picked the K epsilon model. I'm not exactly 100% sure what those are representative of, but so basically they represent your error. So we are going down, going down. Oh, I think there might have been an error. Oh, it's complete apparently. The solution is converged. So all our residuals are pretty low, except the continuity is not great. Like 10 e to the -6 is usually what people consider converged. We can look at the results and see what happens. So if we want to get our drag coefficient, we hit compute. So this is also what I got before, 0.011. So probably that's a good sign. And then we could also double click on our fuselage drag, hit compute. So that's in newtons, 5 newtons. Again, I can't remember off the top of my head, but you do definitely double check symmetry and reference area and what that gets you in terms of forces. Drag coefficient is non-dimensional, so it doesn't matter as long as you give it the right reference area, which we did. But sometimes I think in this case this is total drag because we gave it the total reference area. But definitely something to check. So save this. And we can go to, so that's not our actual results. You can go to our results, and this is kind of how you get like the rainbows, like your CFD post. That's kind of how you get like the nice plots and stuff. Yeah, so if your residuals are kind of high, so I'm kind of concerned about the continuity one because I believe that's important, but the rest of them were really good. Basically, I don't know why this is, if this is still loading. Pretty much what I'm going to do is pull up a pressure plot and see like maybe there's still high pressure areas or like gauge pressure. There's like high gauge pressure close to the edges of the domain, which means we didn't make it big enough basically, and we should make a bigger domain and rerun the same simulation because we're pretty much assuming when we take that chunk that it's big enough that the disturbances on the outside are minimal to none. I don't know why this is not loading. Like why this is black. Okay, I'm not 100% sure why we can't get the results, but I think it might be the graphics card because I'm on the MacLab computer. I've never had this problem, but it seems pretty consistently that it's a graphics card issue. But typically what happens is you'll see your simulation, and pretty much what I would do to check like your visit or kind of just sanity check is insert a contour. So if you hit that button, contour, okay. And I want a pressure contour. I mean, you can have velocity or whatever. Change your domain to your CFD domain. And then you hit apply. And then in theory, we should be visualizing right now, but we can't. But what I would be looking for is high pressure areas on the outside of the domain. It would signify that the domain is not big enough and you should make it bigger and try again. Another thing you can do in your mesh, if you want to do like a mesh convergence, which I won't run this time, but it is something good to know how to do. Go under your mesh body sizing and you go element size and you click this white box P that parameterizes it. So if we go save, we go back to so now we've created a parameter set. If you double click on that, you can basically create like several design points. So now we can say, oh, let's try 2.5 millimeters and let's try oh, that's actually 2.5 millimeters, 1 millimeter. So basically, we can now basically set it to run 3 different simulations with 3 different mesh sizes, and you can see how the results change over the mesh sizes. So if we close that. Oops, I just closed the whole thing. You should also hit the retain button for all the design points you want, which in our case is a mesh element size. Okay, my bad. I totally forgot how to do this for CFD, but there is a way. Okay, yeah, I forget how to do that, but there is a way to change your mesh and get different results out. So yeah, I think that's kind of it for this air brakes CFD. So this is the closed air brake simulation, and then we will have an open simulation, and then hopefully we can, with this data, get the delta between those two. Any more questions?